In this video, we'll talk about electromagnetic radiation and starting with what is an electromagnetic radiation. So, electromagnetic radiation is simply a form of energy that travels in the form of a wave. Now, specifically talking about what is a wave is a disturbance, or we can think about it of the disruption of in a medium. An example that you can think of is, for example, if you drop a pebble in a pond and it creates those like circular waves. These are the disturbances that it created to the medium, which is water. And a wave is a disturbance that transmits energy through space or matter. Now, electromagnetic radiation can also be described as a wave composed of two components, which are oscillating electric and magnetic fields that travel at right angles to each other. So if you look at the picture below here, you can see that the electric component is a wave that travels right here in painted in red, and the magnetic component, which is in blue, both are right angled to each other. Now let's talk about the anatomy of a wave or its components. So let's start with the amplitude of a wave, which is simply the vertical height of a crest. So the crest is the highest part or the peak of a wave. Highest portion or peak of a wave, or the depth of a trough. Okay, so both these are labeled as amplitude. So a trough here is the lowest portion of the wave. Now, wavelength can be described as the distance between two crests. So this right here is a wavelength because it's between the two peaks or the two crests. It can also be the distance between two adjacent troughs. So I can also say that this is a wavelength or this is one wavelength. And the SI units for wavelength is meters. Now, related to the components of the wave, we can also start talking about frequency. So frequency, which is the number of waves that pass through a given point in space in some unit of time. And the units for frequency are either second to the -1 or per second, 1/seconds, or hertz. And I want to give some examples from here, from this picture right here. So I have here the frequency here is 4 cycles per second or 4 hertz. What does that mean? That means in 1 second, I have 4 wavelengths passing through a point and passing through a given point in a certain time or in 1 second. So let's count how many waves. So we have here 1, 2, 3, and then 4. So I have 4 cycles or 4 waves passing through in 1 second. Another example is something with a higher frequency. So if you have a higher frequency, you have more wavelength passing through that point in 1 second. And here it says I have 8 cycles per second. So let's count them together. So 1, 2, 3, 4, 5, 6, 7, and then 8. So I have here 8 wavelengths passing through in 1 second, and so on and so forth. So the more the wavelength passing through, all right, note also that they become smaller. So as I increase the number of wavelength, I will have a higher frequency and shorter or smaller wavelength. All right, now the other thing related to the wave is the speed. All right, and specifically when talking about electromagnetic radiation, all electromagnetic radiation travel at the speed of light. Now, the SI units for speed of light is meters per second, and this it is a constant. The speed of light is given to you on your formula sheet, which is a 2.998 times 10 to the 8th meter per second. And by the way, just for calculation purposes, this is going to be infinite sig figs in calculation. So how do everything that we talked about in terms of the wavelength, the speed of light, and the frequency relate? They're all connected through this particular equation in which the speed of light equals to the wavelength times the frequency. So we discussed before that the speed of light is a constant, and it's 2.998 times 10 to the 8th meter per second. The lambda here is the wavelength in meter, and the frequency is 1/seconds or hertz. But we'll consider it here 1/seconds, not hertz, because it matches the speed of light. Now, if we are going to rearrange this equation right here, C equals to lambda times velocity, right? And therefore, I can rearrange that and say that lambda, oh, sorry, this is not velocity, this is frequency, which is nu. Sorry, this is nu. So I can say that, therefore, nu equals to C over lambda. So I want to again re-explain what I had on the previous slide. So if I have a higher frequency, I will have a lower wavelength, since the frequency is inversely proportional to the wavelength and vice versa. So if I have a longer wavelength, right, I will have a so I'll have a lower frequency, and of course this is a constant. Now, let's talk about the components of the electromagnetic spectrum and what you are exactly expected to know for this class. So, electromagnetic spectrum, to begin with, contains all the possible wavelength of the electromagnetic radiation. Now, you are not required to memorize each and every component. I will specifically point out what you're expected to know. First thing that we are expected to know, the trends in the wavelength and frequencies when it comes to the electromagnetic spectrum, meaning that for example, on the very far left right here, note that I have a longer frequency, longer wavelength, and smaller or lower frequency. Okay, sorry, my handwriting, frequency. And on the far right, we have here smaller or shorter wavelength and higher frequency. So this is the first trend that you are expected to know. Another thing that we are expected to know also is the range of colors in the visible light. So the visible light starts with a lower energy and greater or higher wavelength. So I have here low energy, okay, and higher wavelength, okay, and ends with the violet, which has a higher energy and shorter wavelength, okay. And the range of colors in the visible range are red, orange, yellow, green, blue, indigo, and violet. So it spells Roy Gibiv. And what else? I think this covers everything when it comes to the electromagnetic spectrum. Now let's work on some problems and see how we can apply what we've learned so far in this particular problem. So the first problem here reads, most of the light from a sodium vapor lamp has a wavelength of 589 nanometers and wants you to determine the frequency of this radiation. So in this case, we're going to use C equals the speed of light equals to the wavelength times frequency. All right, and let's see what's given to us in the question. Of course, the speed of light is a constant, which is 2.998 times 10 to the 8th meters per second. The wavelength is 589 nanometers. Okay, note that here the wavelength is in nanometers, while the speed of light is in meters, so we'll have to change to meters. So I can say that in 1 meter, there is 10 to the 9th nanometers. All right, and this is what is left for me to find. And this has infinite sig figs. This has 3 sig figs. So my answer should be 3 sig figs. Therefore, I can say that frequency equals to C over lambda, which is 2.998 times 10 to the 8th meters per second divided by the wavelength, which is the 589 nanometers times 1 meter over 10 to the 9th nanometers. Okay, and this should give me, therefore, I have here frequency is 5.0899 88022 times 10 to the 14th 1 over seconds, or second to the negative 1. And since the lowest number of sig figs is 3, this rounds up to 5.09 times 10 to the 14th second to the negative 1, or I can say even hertz. Okay? All right. Now, I want you to pause the video and think about this question. This is a very conceptual, this is a conceptual question, and which relates the frequency to the wavelength, and it asks which of the following frequencies corresponds to the longest wavelength. So again, we can use C equals to frequency times the wavelength. And therefore, I can say that frequency equals to the speed of light divided by the wavelength. And in this case, what has the longest wavelength, okay, will have the lowest frequency. So among these, choice B has the lowest frequency of all. Now let's talk about the last thing for this video, which is interference and diffraction. So what does interference mean when it comes to waves? That how waves interact with each other, and they have very useful applications in many different fields, such as materials chemistry or biology. And we have 2 types of interference. The first type is constructive interference. Constructive means that, as you can see from the picture, here's the crests and troughs of 2 waves will perfectly align with each other, and they add up to 1 bigger wave. So this is why it's called constructive interference, or sometimes we call it that an in phase, right? And this causes the amplitude, right, of the wave to increase as a result of them adding up together. And if we're thinking about something like light, which has a wave-like nature, it will increase the intensity or the brightness of light in this case. Now, destructive, on the other hand, and I'm referring to this picture. Now, the crests and troughs are not aligned. You can see now that the trough is aligned with the crest of another wave. And as a result, the waves kind of cancel out each other, and they become a single line right here because they canceled out each other, and they are called out of phase. Now, how does this apply to How does this have applications? So, specifically in diffraction, we can use the constructive and destructive interference to identify something like crystals or proteins, right? And in diffraction, um, you have a wave or a light or sometimes an X-ray source, right, that will spread out through destructive and constructive interference through passing from a narrow opening. And this is an example of how diffraction works through constructive and destructive interference. So this is a diffraction pattern. So you can see here that the bright spots right here will result from the constructive interference where they are in phase with each other, where the waves are in phase with each other, while a destructive interference will result in dark spots. And you can think of diffraction patterns as fingerprints to a certain material. So each material will have a very specific diffraction pattern.